As I warned you previously, this section is super long. So this is going to be the second video in 3 required videos, and there is an optional 4th video, which you may want to watch if you want to see a particular type of example. In this particular one, we've already learned how to parameterize a surface, and we learned that a regular parameterization, which results in a smooth surface, is one in which the directional derivatives r with respect to u crossed with r with respect to v is not the 0 vector for any point on the surface. Now we want to use this information in order to find the area of a surface. And once we have the area of a surface, we'll be able to use this to define what we mean by a surface integral. In this video, we focus on surface area and we focus on surface integrals for scalar valued functions. We have a few learning objectives, which we're going to cover in this section. Namely, we're going to describe the surface integral of a scalar valued function over a parametric surface. And we're going to use a surface integral to calculate the area of a given surface. Then we're going to solve an application problem towards the end of this video. Allow me to share my screen so we can get started. We're going to start by discussing what we mean by surface area of a parametric surface. Now, when we're talking about a parametric surface, we could have something like, say, a hyperbolic paraboloid. It's not a solid, it's not a 3-dimensional thing. It's really, in a sense, a 2-dimensional thing that exists in 3-dimensional space. So it has length and width, but no height or depth to it. So at any particular point, it's sort of, 2-dimensional. And we just know that if we could flatten it out, we could compute the area of it. So we can think of this as sort of like a sheet flapping in the wind. If there were no wind and we could lay the sheet out flat, we could compute its area using the formula for the area of a rectangle. In order to find the surface area of a 2-dimensional surface in 3-dimensional space, we're going to do the calculus thing, which is to cut it into a lot of tiny little pieces. We're going to use the parameterization that we learned about in the previous video and cut them into tiny pieces along the 2 parameters, u and v. So we'll have a delta u and a delta v. As long as they're small enough, we'll be able to approximate the area of a tiny little section of it with a tiny section of the tangent plane. We're not going to cover this in great detail, although we do go through the basics. You can find more detail if you want in the textbook, pages 672 to 763. What we're doing is, again, we're defining parameters u and v to define our surface. We're representing the surface as r of u and v. And we need it such that the normal vector is not the 0 vector. We find the normal vector by computing the directional derivative, the partial of u of r with respect to u, and the partial of r with respect to v, which are 2 tangent vectors lying within the tangent plane, and then we take their cross product to get a normal vector. When we think about it, if we have the parameter domain, which is the domain for u and v, on the domain for u and v, we can cut it up into tiny little rectangles. On the parameter domain, it is flat. However, when we translate this through our parameterization into the actual surface, the surface bends. The surface is not flat. It's sort of like this hyperbolic paraboloid. So what we're doing is we're projecting what was a flat division of the UV plane onto the curved surface. So what were flat grid lines in the UV plane become curved lines on the actual surface. But we can still talk about the IJ sub-rectangle, if you will, by looking at the ith position for U and the ith position or jth position for V, and then translating that rectangle from the UV plane into the curved surface. We can call that tiny subsection of the surface capital S sub ij. And then we can take a particular point within that curving sort of rectangle. So it's not flat, it's not truly a rectangle, but curved rectangle, and call that point P sub ij. Now, in the textbook, they use the lower left-hand corner, but in fact, it could be any point within that small subsection of the surface. What we're doing, of course, is we're going to allow U and V to vary while holding the other constant. So for example, if I hold V to be constant at V naught, but I allow U to vary, then I get this blue line in the UV plane or the parameter domain. Over on the surface, it translates into this curving line or curve in three-dimensional space on the surface. I can do the same thing by holding U constant and allowing V to vary, which will give me this orange line here in the UV parameter domain. And that translates into this line here. And then, of course, what I'm doing is I'm finding the directional derivative along that particular line. So I can call the partial derivative of r with respect to u t sub u, which represents the vector in the tangent plane. And I can call the partial derivative of r with respect to v t sub v, because it is that vector in the tangent plane. So both of these are lying within the tangent plane. And if I use a very small subsection of this, it's very close to the surface itself. So long as I'm very close to the surface, I can use the tangent plane to approximate the area on this curving, rolling surface. Let's take a look now at what this might look like if we just look at that small subsection of the surface, S sub ij. S sub ij, of course, is curved, right? It's on some kind of surface in three-dimensional space, but the surface is not flat. So when I look at S sub ij, I have dotted above it the section of the tangent plane that it corresponds to S sub ij. So I can take delta V and multiply it by that directional derivative, the partial of r with respect to V, or T sub V. I can do the same thing for the directional derivative where I allow U to vary but hold V constant, which is the partial of r with respect to U. So I'm scaling each of these directional derivatives by delta U and delta V so that it corresponds exactly with the section that I'm taking out of my original surface, which is on this picture here. So I'm taking this orange square, which on the surface is S sub ij, and S sub ij curves, but it's very close to that section of the tangent plane lying above it at point P sub ij. Now, we know, of course, that we can find the area of a parallelogram spanned by two vectors by finding the magnitude of their cross products. And what we want to do is approximate the surface area of the surface. So the surface isn't flat, but what we're going to do is cut it into tiny, tiny little pieces. And we're going to approximate each piece by the tangent plane at a particular point in that piece. And then we're going to find the area of the parallelogram on the tangent plane and use that to approximate that tiny subsection of the curving surface. So once we have this, we can write down the formula for the area of that small curved surface. Now, the curved surface, of course, is the one pictured here in teal. It's not flat, but the orange vectors and the dashed lines are on the tangent plane, and that is flat because the plane is, well, a plane. So it is flat, and I can find the area of that parallelogram by taking delta u times the partial of r with respect to u at some point in that subsection, p sub ij, crossing it with delta v times the partial of r with respect to v at the same point, p sub ij, in that subsection. When I take their cross products and find the magnitude, that gives me the area of the parallelogram. Now, I can use that area to approximate the area of the curving surface. Now, delta u and delta v, of course, are constants. So they can be brought out of the cross product, and this gives us the magnitude of r with respect to u crossed with r with respect to v times delta u delta v. I know it sounds like we're about to integrate, and we are about to integrate. Here's how we find the surface area of a parameterized surface. This is, in fact, a surface integral where our function is allowed to be the number 1. So you'll see right here that what we're doing is we're saying the surface area, if we add up all of these little areas over this entire region, then I've got the partial of r with respect to u crossed with a partial of r with respect to v, find the magnitude, and integrate across the parameter domain D, all the values that u and v are allowed to have to substitute into the parameterization. Now, in order for this to work, we have to assume it's a smooth parameterization so that the cross product is not the zero vector. Now, this is the same as multiplying this magnitude by 1, and that makes it a surface integral. So when we have a surface integral, we're actually computing a double integral over the parameter domain where u and v are varying. And we have here the partial of u and the partial of r with respect to v, as we normally define these. And this should give us the surface area. So let's take a look at example 1. In example 1, we want to find the surface area of the surface with a given parameterization, u plus v, comma, u squared, comma, 2v. Now, we spent some time in the last section trying to predict what they look like, but of course you have CalcPlot 3D. So my advice is simply to go ahead and plot the parameterization so you can see what it looks like. Now we have restrictions on u from 0 to 3 and restrictions on v from 0 to 2. Let's go ahead and take a look at CalcPlot 3D so we can get an idea of our shape. So it looks, well, it looks almost flat, but if you hold it at a certain angle, you can see that no, in fact, it's sort of curving there at the end. So it almost looks kind of like an old-fashioned sled that is curving up at the end of it. So it is almost like a plane, but it's not totally flat. It's curving. And we want to find the area of this region. Now, when we do this, we are limiting u to go between 0 and 3 and v from 0 to 2. So let's go ahead and change that. 0 to 3. I think it's actually graphed with those. And 0 to 2. Yeah, it's actually, that is the correct graph. All right. So we've got our surface here that we're trying to find the area for. We allow the function to be the number 1. And now we need to find the partial of r with respect to u crossed with the partial of r with respect to v. We're given the parameterization, which is up here, u plus v, u squared, comma, 2v. So the first thing we need to do is find the partial derivatives, the directional derivatives, cross them together, find the magnitude, and then substitute them into an integral. Let's go ahead and start with the first part. We need to find, for example, r with respect to u, which is going to be 1, comma, 2u, comma, 0. And then we need to find r with respect to v, which is going to be 1, 0, 2. The next thing you need to do is find r of u crossed with r of v, and then find the magnitude of that. Go ahead and pause the video while you work out the cross product of these two vectors. Then turn the video back on and we'll continue to the next step. And notice here that you have the choice to either expand along a row or column, or to repeat columns 1 and 2 to the side and use the major diagonals minus the minor diagonals. Pause the video now to work out the cross product. When we find the partial of r with respect to u crossed with the partial of r with respect to v, we end up getting 4u, -2, -2u. Again, you're marking out column 1 and row 1, and the 2 by 2 determinant is 4u minus 0 for the first component, then minus j hat times 2 minus 0, so minus 2j hat. And then k hat is 0 minus 2u, so minus 2u in the k hat. Then to find the magnitude, you square each component, add them together, which gives you 20u squared plus 4, all under the square root. You can factor out a common factor of 4 to get 2 times the square root of 5u squared plus 1. Then we're going to find the surface area by allowing our function to be a positive 1 and computing the double integral over the parameter domain, where u varies from 0 to 3 and v from 0 to 2. Because our constants or limits of integration are constants, we're integrating over a rectangular domain in the parameter domain, so it doesn't matter whether you integrate with respect to u first or with respect to v. The integral that you should have will look something like this. The surface area is equal to the integral over the parameter domain of 2 square root of 5u squared plus 1 with respect to the area. And I'm choosing to do v first, since it doesn't depend on v. I'm just going to get another constant of 2 multiplied by the current integrand. And then I will be able to integrate it with respect to u. Go ahead and pause the video to work out this integral, then turn it back on so we can compare our results. I will give you a hint that you're probably going to need trig substitution on this one. So when we worked this one out, the first thing I did was integrate with respect to v. So I got v evaluated from 0 to 2 with the 2 square roots of 5u squared plus 1, simply a constant. That gave me a new integrand of 4 square root of 5u squared plus 1. Then I did a trig substitution where square root of 5 quantity times u is tangent of theta. Then I solved for u to get 1 divided by the square root of 5 times tangent of theta is u. So I found du to be 1 divided by the square root of 5 multiplied by secant squared of theta d theta. Then I rebuilt what was under the radical, the 5u squared plus 1, by squaring both sides and getting tangent squared of theta plus 1, which gives me secant squared of theta. When I substitute this into the integrand, I did not change my limits of integration this time because it would have been more difficult. So I kept them u values, but I wrote u equals 0 to u equal 3. 4 square root of secant squared of theta, which will give us a secant of theta, times 1 over square root of 5 times secant squared of theta d theta. This gives us a constant factor of 4 divided by the square root of 5, and the integrand of secant cubed of theta d theta. Now you can integrate this one, of course, using integration by parts and trig integrals. And when you do, you come up with the following result: that the integral is 1/2 secant of theta tangent theta plus the natural log of secant theta plus tangent theta. You can also use an online integral calculator or an integral table to get the value of secant cubed. we still have our 4 over the square root of 5 as a constant factor. Now I want to evaluate between u equals 0 and u equals 3, but it's written in terms of theta. So I draw a triangle, I label theta, and I use my basic substitution equation that tangent of theta is equal to root 5 over u to label 2 of the sides of the triangle. Tangent is opposite over adjacent, so the opposite side is root 5 times u, and the adjacent side is 1. Then I can use the Pythagorean theorem to find the missing side, which is the hypotenuse, which gives me square root of 5u squared plus 1, which is what I had in the original integral, so I know I'm on the right track. Then I can evaluate secant of theta. I already have tangent of theta as root 5 times u. Secant of theta is hypotenuse over adjacent, so it becomes the square root of 5u squared plus 1. This enables me to substitute that in place of each secant of theta and to substitute root 5 times u for each tangent of theta. Now I have it rewritten in terms of u, so I'm ready to go ahead and substitute in the values. There's quite a bit of simplification that has to take place in here, and at least one of the terms goes to 0. When I do this multiplication or substitution and I work out each one, I also get a natural log of 1, which is also 0. So my final result is 6 times the square root of 46 plus 2 divided by root 5 times the quantity natural log of quantity root 46 plus 3 root of 5, which is about 44.06. Now, what does this mean? This is the area of that surface. So remember that we're looking at the surface in CalcPlot 3D, and what we've determined is that it's about 44 square units in surface area. Let's now use the surface area to find the surface area of a solid of a volume of revolution. So we know from Calculus 2 or Calculus 1 that you can take a function and revolve it around either the x or the y-axis to produce a solid of revolution. We found volumes previously, but now we want to find the surface area of that solid of revolution. So what we're going to do is we're going to have to parameterize our curve and parameterize the surface. Now, an easy way to parameterize the surface, if it is a function of x and we're revolving around the x-axis, is to allow x to be, well, x, and theta to be our second parameter. So how are we getting this? When we do this, we have x times f of x cosine theta, f of x sine theta. So the reason we're getting those is that when you revolve it around an axis, you produce disks at each value of x. And each disk, of course, has a circular cross-section. And when you look at it, because it's circular, you know that you have some function value at that point, which is giving you the radius of the circle. So when you revolve it, then you get that y is equal to the function value times cosine theta, and z is equal to the function value times sine theta. In other words, you're creating a example of a circle which has been parameterized in terms of x and theta. Now, when we do this, if we want to go all the way around, then we will integrate, allowing x to vary from a to b, and then theta to vary from 0 to 2 pi. Now, in Calculus 2, we did not do examples where we didn't revolve it completely, but now that we are representing it as a parameterized surface, we are actually able to go only part way around and still find the surface area of the part that's gone all the way around. Now, the revolving produces a solid, but the surface area is simply the area of the surface of it, the outside of it, not the whole solid. So when we take a look at this, you can see right here that what you've got is a circle, and on the circle, you've got f times the cosine of theta and f times sine theta, which is giving you, of course, the ability to parameterize it as a surface. Let's go ahead and do an example where we find the area of the surface of the solid of revolution obtained by rotating the curve y equals sine x, where x varies from 0 to pi about the x-axis. So in this case, we're going to rotate all the way around. If we rotate all the way around, then we want to integrate where theta goes from 0 to 2 pi, and x is going to vary, in this case, from 0 to pi. We parameterize our surface as x, f of x times cosine theta, f of x times sine theta. This is basically r cosine theta, r sine theta, where r is the radius of that disk, which is created by the function value at that point. In order to do it, we need to find the cross product of the directional derivatives, get the magnitude, and then evaluate the double integral. Go ahead and pause the video now to work this one out, and then turn the video back on and we'll compare our results. So this particular problem is a really long integration process. So let's go through the basics of finding the surface area of this solid of revolution. So we rotated the curve sine of x about the x-axis, fully revolved it, so theta from 0 to 2 pi, x varying from 0 to pi. So if we want to, we can take a look at what this revolved region looks like out on CalPlot 3D, if I can find my right thing. So here it is right here. So you can see that x is going from 0 to pi. And when I'm looking at this particular one, let me see if I can get it back to a normal orientation. So x is from 0 to pi, and it's revolved all the way around. And what I'm trying to find is the amount of paint that would be required to paint this surface, or the amount of wrapping paper required to just cover it with no overlapping. So the first thing we need to do is parameterize it. And when we parameterize a solid of revolution, when we're integrating with respect to x, we let x be the first component, the function times cosine theta as the second component, so sine x cosine theta, and the function times sine theta as the third component, sine x times sine theta. And this gives me, of course, my parameterization of the curve. So once I have the parameterization of the curve, then I want to go ahead and find the directional derivatives, the partial of r with respect to x and the partial of r with respect to theta. Once I have those, I'll find the normal vector by crossing them together. So the derivative, partial derivative with respect to x gives me 1 cosine x cosine theta, cosine x sine theta. The partial with respect to theta gives me 0, negative sine x sine theta, sine x cosine theta. Now I take the cross product so I can get the normal vector. When I do the cross product, I write it as a pseudo 3x3 determinant matrix. So I have ijk as the first row, and one of the directional derivatives is the second row, which I chose the partial with respect to x, and one of the directional derivatives as the third row. I expanded along row 1, so I have I hat times the 2x2 determinant formed by the lower right 4 items. So I get cosine x sine x cosine squared of theta minus a negative sine x cosine x sine squared of theta. Now both of these have a sine x cosine x factor, and when I factor it out, I get cosine squared theta plus sine squared theta, which is 1. So multiplied by the I hat, I end up with sine x cosine theta. Then I form the second component by taking minus j hat, since it's in the 1, 2 position. First row, second column, it's an odd, 1 plus 2 is 3, so it's negative. And then I form the 2x2 matrix, 1 times sine x cosine theta minus cosine x sine theta times 0, which just zeroes it out. So I get a negative sine x cosine theta for my second component of the normal vector. Then I mark out column 3 and row 1, and I get 1 times negative sine x sine theta minus cosine x cosine theta times 0, which gives me negative sine x sine theta for my third component of the normal vector. Then, in order to find the area, I compute the magnitude of that normal vector by squaring each component and adding them together. When I square the last two components, I get a common factor of sine squared of x, and when factored out, it gives me cosine squared theta plus sine squared theta, which again is equal to 1. So this gives me sine squared x cosine squared x plus sine squared x. There's a common factor of sine squared of x, which I can factor out, giving another factor of cosine squared x plus 1. I can take the square root of each factor, and the square root of sine squared gives me the absolute value of sine of x, multiplied by the square root of cosine squared x plus 1. With the plus 1, I'm stuck. I can't do anything because of the addition. So this is going to become my integrand. When I form the double integral, notice that I switched from absolute value of sine x to regular sine x, because x is varying from 0 to pi, which means it's going in quadrants 1 and 2, where sine is always strictly positive. Since it's strictly positive, I can simply drop the absolute values. Now, in order to integrate this, I need to do a u substitution. My u substitution is going to be for cosine x, not cosine squared x plus 1. If I chose the entire radicand, then I would get 2 cosine x times negative sine x for my actual derivative of it. And I don't want that because I only have sine x on the outside. So I choose instead for u to just be the cosine of x. Then the derivative of it is negative sine x dx. So I'm going to get a negative thrown in because I only have sine x dx. I can change the limits of integration. When x is 0, u is the cosine of 0, which is 1. When x is pi, u is the cosine of pi, which is negative 1. So I had to put in a negative because I didn't have it as part of my du. And I'm integrating from 1 to negative 1. And since this isn't the normal order, and I have a negative as a factor in the integrand, I can switch the limits of integration. This makes it u squared plus 1 under the square root. And now we're integrating with respect to u first and then d theta. In retrospect, I probably should have done d theta first and then dealt with the u's. It would have saved me a lot of writing. So when I got down to this point, this, of course, is a trig substitution. So you let u be tangent of some other angle. I've already got theta in u, so I just chose alpha. You could choose beta, gamma, whatever you want. Then I go ahead and take the derivative, which gives me secant squared of alpha d alpha, and I build what's underneath the radical, u squared plus 1, by squaring tangent and adding 1. Tangent squared of alpha plus 1 is secant squared of alpha. So I replace u squared plus 1 with secant squared of alpha, and I replace my du with secant squared alpha d alpha. Now, I don't want to change the limits of integration. I do want to come back to u. So I left them u from negative 1 to 1, and notice that the negative is gone because I reversed the order of integration. This, of course, is going to give me secant cubed of alpha d alpha. And again, we've already done this one once today, so we'll go ahead and simply write up the result, which is 1/2 secant alpha tangent alpha plus natural log of the absolute value of secant plus tangent. When we do this one, we want to go ahead and use our substitution equation that u is tangent of alpha to label two sides of the alpha triangle. This tells us the hypotenuse is the square root of u squared plus 1. So we can replace all secant thetas or secant alphas with square root of u squared plus 1. When we replace that into the integrand, and notice that I haven't evaluated the outside integral yet, I want to evaluate from u equal negative 1 to 1, and it's now written in terms of u. So I can directly substitute. You got to be very careful with the negatives here because there's just a lot running around. And when you're done, you should end up with 1/2 times the entire quantity, 2√2 natural log of √2 plus 1 minus natural log of √2 minus 1. Now you can use the college algebra identity that the difference of natural logs is the natural log of their ratio. So the positive one moves to the numerator and the negative argument moves to the denominator. And then I can distribute the 1/2, giving me √2 plus 1/2 natural log of the quantity √2 plus 1, all divided by √2 minus 1. Finally, I integrate with respect to theta, and I don't have anything that depends on theta, so all of this is just a constant, like 5. And so I get 5 d theta, which is 5 theta, and then I'm going to evaluate from 0 to 2 pi, which gives me 2 pi multiplied by my constant. And when you do this, it comes out to be about 14.42. So what we're saying is that the amount of paint that will cover this is 14.42 square, whatever, square units, right? Let's now go ahead and take a look at a surface integral of a scalar valued function. Now that we've covered how to find surface area, we want to more formally define the surface integral. In a lot of ways, what we're doing in chapter 6 is we're extending what we learned in chapter 1 with the fundamental theorem of calculus into higher dimensions. In calculus 1, we started by integrating over a line segment on either the x or the y-axis from x equal a to x equal b, or y equal c to y equal d. Then in this class, we took a curve and we chopped it up and we integrated over the curve. Now we're taking a surface, we're chopping up the surface and integrating over the surface. Again, the idea is to chop into tiny pieces, compute the area of the tiny pieces, take a Riemann sum to sum them up, allow the area of each little piece to approach 0, and take the limit of that. And that should give us the exact whatever we're looking for. Now, in this class, we're doing pretty much the same thing as we did in Cal 1. And what we're going to do now is try to compute what happens when we do a function evaluated on a surface. So in the surface area, we allowed our function to be the number 1. But suppose we want to evaluate some function over a surface. In that case, we need to integrate the function over the surface. So again, we're going to cut it up into tiny pieces, and we're going to find the little area of each little piece and multiply that by the function value. The problem is, even though it really doesn't matter for a surface integral what shape those tiny pieces are, they could be circles, they could be trapezoids, they could be rectangles, they could be whatever we want. In practice, it makes it very difficult to compute if we don't have a geometric formula to use. So while in theory, it doesn't matter what the shape of each of those little cut up pieces of the surface are, in practice, what we're going to do is we're going to go ahead and compute the surface area part using the same parallelograms we did when computing just surface area, which is those little parallelograms. So we're approximating the little section of the curved surface with the parallelogram from the tangent plane. Now, remember that in the textbook, they often use t sub u in place of the partial of r with respect to u, and t sub v in place of the partial of r with respect to v, where r is the parameterization of the surface. Now, when we did surface area, we computed the double integral of the magnitude of the normal vector with respect to the area differential. In this case, what we're going to do now is we're going to add in some function that needs to be evaluated across the surface. So we'll have to convert our function from being a function of x, y, and z to being a function of our parameterization of the surface. So I'll have to compute f of r of u and v, much the way we did with line integrals when we converted a line integral f dot ds with the arc length differential into a single integral with respect to the parameter t by rewriting the function as f of r of t. Now we're going to do the same thing, and we're going to parameterize our function by writing f in terms of the parameterization. Once we do that, we'll be able to take a Riemann sum as the number of cuts on our particular thing increase in value. The number of cuts goes to infinity, which means the width of each cut is going to 0. And we're going to evaluate this function of the parameterization multiplied by the magnitude of the normal vector. And this will be with respect to A. So in actual fact, you've been doing a surface integral. The surface area is a surface integral where the function is simply the number 1. Now, this is our first formula, what we're looking at here, which is going to give us f of r of u and v multiplied by the magnitude of that cross product. There is another way of thinking about this. It's not covered in the textbook, but there is another way of doing it without the parameterization. But I will warn you that this method involves the square root. And the square root often makes it difficult to actually do the integration. So in most cases, it is far better to parameterize the surface and use f of r of u and v multiplied by the magnitude of the cross product. Let's take a look at what this second method does. In this second method of defining what a surface integral is, let's just start with a fairly simple, straightforward surface in three-dimensional space. We can call it S, and it's projecting down into the XY plane. Now, it could just as easily project into the YZ or the XZ plane. It doesn't matter, but it's projecting into one of the coordinate planes. So we've got this region D down here. And because it's a relatively simple region, the region D is a polygon. So X is going from A to B and Y is going from C to D. And this is giving us basically a rectangle down there in the plane. Now we can represent the surface as some function of X and Y. So we have an equation Z equals blah, blah, blah with X and Y in it. So our surface is given by this equation, which we'll call G of X and Y. So since Z equals G, we could subtract the Z to the other side so that we get G of XY minus Z equals 0, as we did much earlier this semester. Then we can write the surface integral as this double integral instead. So the surface integral with the differential d capital S, which is not the arc length differential, this is the surface area differential, becomes f of xy, g of xy, where z is that function, multiplied by the square root of the partial of g with respect to x squared, plus the partial of g with respect to y squared, plus 1. Now you may be looking at this going, how in the world is that related to f of r of u and v multiplied by the magnitude of the normal vector? How can this be the same? Well, our ds, of course, is coming from this part right here, saying that we have the partial of g with respect to x squared, partial of g with respect to y squared, plus the partial of g with respect to z squared. But g is equal to z, so the partial of z with respect to z is just the number 1, which is why we get a 1 here. Now you have to be careful because the integral on the left is a surface integral, but the integral on the right is a regular double integral. So what we want to do now is go ahead and figure out where this is coming from. Now it is possible, as I said before, to project not just into the XY plane, but to project into the YZ plane or the XZ plane. If you do that, then it does change the format of this differential a little bit. So in that case, if you're going to project into the XZ plane, then you've got Y equal to some function. So your function is G equal to Y. So then you have X and Z as the first and third components respectively. And your partial of G with respect to Y would just be 1, since G of X and Z is equal to Y. So that would be this part here, which results in this right here. And the second one is projecting into the YZ plane. And if you project into the YZ plane, then you're setting X to be equal to G of Y and Z, which means the partial of G with respect to X is just the number 1. So you can do it into any of the planes, whichever one you want. Now, let's go back to the original one where we're projecting into the XY plane, and let's see how this very complicated integrand, this double integral, how does this relate to f of r of u and v multiplied by the magnitude of the cross product? How do those turn out to be the same thing? So we're going to parameterize our surface as we've done before, but we're just going to use a straightforward one. So we're projecting into the xy plane. So we have z equals some function of x and y. So we parameterize allowing r of x and y to be x, y, and whatever that function is, z equal to x squared plus y squared minus 2x plus 13, something like that. So then we can take the partial of this parameterization with respect to x, which is going to give us 1, 0, and the partial of g with respect to x, whatever that function is. And then we can take the partial with respect to y, and the partial of x will just be 0, partial of y will be 1, and then we get the partial of g with respect to y. So we have two directional derivatives, which you know lie in the tangent plane. So we're going to take their cross product. Now you can write it in different ways. And in this case, what we've got is 1, 0, partial of g with respect to x, 0, 1, partial of g with respect to y. And again, it doesn't matter which order you cross them in. One will give you the normal vector in this direction, one will give it to you in that direction. When we compute the semi-determinant of this sort of 3 by 3 matrix, we get 0 minus the partial of g with respect to x in the I hat direction. And crossing out column 2, we get minus the partial of g with respect to y minus 0 in the j hat direction. And in the k hat direction, we mark out column 3 and we just get 1 minus 0 or 1. So this tells me that this r sub x crossed with r sub y is the partial of g with respect to x squared plus the partial of g with respect to y squared plus 1. In other words, the magnitude of this cross product is exactly that square root that we found in that formula. So in other words, they're the same, all right? They're really the same method. You can use either one, but I will warn you that the formula with the square root in it often becomes very difficult to actually integrate. So here's what it looks like when you're projecting into the x plane. So you have it solve for z, and you would use this formula right here. And then the one down here, the first one, is the one where you have it solve for y. So y is your g of x and z, and you would use this formula. Or you could have it solve for x, then x becomes your g of y and z, and you would use this formula here. Most students find this far more complicated, having to learn sort of 3 different formulas as opposed to the one formula from the parameterization. The formula from the parameterization is a little bit cleaner to my mind and more reminiscent of what we did when we computed line integrals. we're substituting the parameterization into the function and multiplying by the magnitude of something, in this case, the magnitude of the normal vector. This is the method that I recommend that you use. Let's go ahead and I'll show you why. You'll see why in just a minute. Let's take a look at example 3. So in example 3, we're given a surface with parameterization v comma u squared plus v squared comma 1. U varies from 0 to 2 and v varies from 0 to 3. So if we want to look at this shape on CalcPlot 3D, we're wanting to integrate a surface integral. Now you may be wondering, well, what is the surface integral? Well, it depends on what the function represents. If this function represents, for example, the density of the material per unit area, then when we integrate across the surface, we'll get the mass of whatever object that we have. So it depends on what your function of x, y, and z represents. In this case, my function of x, y, and z must be x squared minus z. When I look at this curve out on CalcPlot 3D, and let me get to it, there it is right there. It looks, well, it's kind of curved. It looks kind of flat. It's kind of coming up like that. So it definitely has a curl to it, but it looks sort of like part of a plane, if you will, but curled ever so slightly on one end of it, right? Let's now go ahead and use method 1. So we want to use the one that I think is really the best for students. So we want to parameterize our surface, which they've already done for us. Then we want to substitute the parameterization into our function. And our function was x squared minus z. So our x becomes the v and z is 1. So we're going to get v squared minus 1. And then we're going to compute the directional derivatives, the partial of r with respect to u and with respect to v, find their cross product, get the magnitude, multiply that by the parameterization of my function, and then integrate it over the double integral, the parameter domain, where u varies from 0 to 2 and v varies from 0 to 3. So in order to do this, the first thing that we want to do is find those directional derivatives. So here's the parameterization again, v u squared plus v squared and 1. So let's go ahead and write down what the partial with respect to u is. So in this case, it's going to be equal to 0, 2u, 0. And then we can compute the partial with respect to v. And the partial with respect to v is going to be 1, 2v, and 0. Now, since we're evaluating our function, x squared minus z, then we need to parameterize that using the surface parameterization. So we're going to substitute these values into our function. So x is going to be our v squared. So we're going to get v squared plus 1. So f of r of u and v is going to become v squared minus 1 from the parameterization that you see up here. All right. Now, once we have that, we want to compute the cross product of the two directional derivatives and get the magnitude. So go ahead and pause the video and do just that much, then turn the video back on and we'll set up the integral so that you can integrate next. So now that we have our two directional derivatives, we want to find their cross product. Now recall that we represented x squared minus z as v squared minus 1, converting x squared minus z using the parameterization. When we form the pseudo 3x3 matrix, we get ijk 0, 2u, 0 for row 2, 1, 2v, 0 for row 3. Again, the order of rows 2 and 3 really doesn't matter. You're going to get the same value in the end. When we do this, we're going to cross out column 1 and row 1, and we get 0 minus 0 in the I-hat direction, or nothing for the first component. Cross out column 2, row 1 with a negative coefficient. We get 0 minus 0, or 0 again for the second component. Cross out column 3 and row 1. We get 0 minus 2u. So we get negative 2u for the third component. Then we find the magnitude of this normal vector by squaring each component and adding them together and taking the square root. This gives us the square root of 4u squared, which is 2 times the absolute value of u. Now we need to put that into an integral. When we put it into the integral, our surface integral of f of x, y, z with respect to the surface area differential d uppercase letter s, this converts to f of r of u and v multiplied by the magnitude of the cross product in a regular double integral with respect to du and dv. In this case, we substitute v squared minus 1 for f of r of u and v, and 2u in place of the magnitude of the cross product. Now you may wonder what happened to the absolute values. U varies from 0 to 2, so it's always non-negative, so we can drop the absolute values. Go ahead and pause the video to do the integration, and then turn the video back on, and we'll compare our results. Once you have done the setup for the integral, I went ahead and integrated with respect to u first, and that gave me u squared over 2, which canceled the factor 2, and gave me v squared minus 1, the quantity, times u squared, evaluated from 0 to 2. This would give me a factor of 4, which I multiplied by v squared minus 1, giving me 4v squared minus 4 for the new integrand. Then I integrated this with respect to v to get 4/3 v cubed minus 4v and evaluated between 0 and 3. The final value I got was 24. Now again, what the 24 represents depends on what the function represents. If that had been a density function, then this would represent the weight, the mass, the number of kilograms of that particular shape. Now we want to take a look at example 4. In example 4, we want to calculate a surface integral with a function of x minus y, where the surface is the cylinder given by x squared plus y squared equal 1, so it has a radius of 1, where z varies from 0 to 2, and we want to include the circular top and the circular bottom. Now, in order to include it, we have to parameterize each surface separately, because in this case, it's more or less a right circular cylinder. And we know that where the circle at the top meets the sides of the cylinder, much like you would have on a Coke can, we have a crease, an edge, if you will. And we have the same at the bottom. So we have 2 places on this surface that are not smooth. So we're going to have to parameterize the top, parameterize the bottom, and parameterize the sides, compute each separately, and add the result together. Let's take a look at this surface out on CalcPlot 3D so you can see how to develop this surface. We need to parameterize the top and the bottom. We know that it is x squared plus y squared equal 1, giving us the sides. That means the tops are circles of radius 1. So we can use polar coordinates, r cosine theta and r sine theta, to get the top. The top is going to be given by cosine u, or where to go? Here it is. U cosine v, u sine v, and 2, where we're using u, of course, as the radius and v as the angle. And we're going at a height of 2 because the circular top is when z equal 2. The parameterization for the bottom is actually identically the same. The only difference is that the z value is 0 because the bottom of this is down there in the XY plane. So if we rotate up, you can see the bottom there. Now, the next question is, how do we parameterize the sides? For the sides, we want to take a circle in the plane and draw it up along a plane parallel to the z-axis. So in that case, we set x to be cosine u, y to be sine of u, giving us a circle of radius 1, and we draw it along the z-axis. And this will give us our parameter. Notice that each of these has a limitation on the values of u and v, which in the case of this particular parameterization, u is going to vary depending from 0 to 1, and v is going to go from 0 to 2 pi, except on the first parameterization, where u represents the angle, and we want the entire way around the cylinder. So we set u from 0 to 2 pi, and v goes from 0 to 2 because we're using the height. Let's go ahead and take a look now at these different parameterizations. Here are the ways that we parameterize the top and the bottom and the sides. Since the top and the bottom are circles, we can parameterize those using basically polar coordinates at a particular height. So r cosine theta, r cosine, or r sine theta, and r is u and theta is v. So the top is at 2 and the bottom is at 0. In both the top and the bottom, u is going to vary from 0 to 1 because we want the entire top. So it starts at the center and works its way out. And we want to go all the way around the circular top. So we have v vary from 0 to 2 pi. The cylindrical tube itself, however, is done instead here with cosine u sine u v, using in a sense sort of cylindrical coordinates, where r here is constantly 1. So we have cosine u sine u giving us a circle of radius 1, and then we draw it up along the v-axis or the z-axis by having the third component be v. Then we're going to vary the angle from 0 to 2 pi so that we go all the way around the cylinder, and we want the height of the cylinder to go from 0 to 2. So notice that the parameters are not the same. So our limits of integration are going to be different between the top and bottom, which are the same, and the sides, which are going to be different. Let's let the top be S1, the bottom be S2, and the cylindrical sides be S3. What we need to do now is we have a parameterization for each of these surfaces. So we now need to go ahead and compute the cross product, giving us the normal vector. So we need to take the partial with respect to u and v on each of the 3 different parameterizations in order to find that cross product. Then we'll go ahead and parameterize the function. And remember, our function in this case is x minus y. So we'll parameterize that according to the parameterization before we set up the integral. Let's just do one piece at a time. Let's go ahead and set up what the function is going to be. And again, it's x minus u, and I have the parameterizations written here. And then find the directional derivatives, the partials of the parameterization with respect to u and v, their cross product, and their magnitude. Then go ahead and turn the video back on, and we'll continue our study of this surface integral. So let's take a look at surface 1, which is the top, which is parameterized by u cosine v, u sine v, and 2. And again, we need the radius to vary because we want to go from the center of the circle out to the edges. In this case, u varies from 0 to 1, giving us from the center to the edge of the circle, and v goes from 0 to 2 pi, so we go all the way around. If I take the partial with respect to u, I get cosine v sine v 0, And the partial with respect to v is negative u sine v, u cosine v, comma 0. Then I take their cross product, getting 0, 0, u. And when I find the magnitude, I'll get the absolute value of u. Now I can go ahead and put this into my integral formula down below, which you'll see here, where v varies from 0 to 2 pi, u from 0 to 1. And then I'm finding the function, which of course was x minus y, which in this parameterization is u cosine v minus u sine v, times the magnitude of the cross product, which is u. Now you may wonder what happened to the absolute values, but u is strictly non-negative, so I can drop them. And then I can integrate the double integral to find the value of the surface integral on the top surface. Let's take a look at the second parameterization, which is the bottom edge of this cylinder, which is the bottom circle. So our parameterization here is similar, u cosine v, u sine v, 0, where the z value is 0 for the bottom of the cylinder, u again varying from 0 to 1, and v from 0 to 2 pi. Notice, however, that when we take the partial derivatives of the parameterization, we get exactly what we got for the top, because the only difference was the height at which the circle appeared. In other words, it's the same surface, just in two locations, one at z equals 0 and one at z equal 2. Since it's the same surface, it makes sense that we're going to get the same normal vector, which is 0, 0, u, and the magnitude will be the absolute value of u. When we substitute this into the integral, we're going to get exactly the same thing as we get for the top. So basically, the top and the bottom are two surfaces that are identical, just in different locations. Let's now take a look at the third surface, which is the sides of our cylinder. So the red part of this Coke can, not the top, not the bottom, but the sides. This parameterization is different. It's cosine u, sine u, v. V varies from 0 to 2, so we get the full height of the sides, and u varies from 0 to 2 pi. This sets our radius to always be 1, but it gets us all the way around the cylinder. The partial derivative of the parameterization with respect to u is negative sine u, cosine u, 0. The parameterization with respect to v is simple, 0, 0, 1. When we find the cross product of these two vectors, we get the normal vector as cosine u, comma sine u, comma 0. To find the magnitude, we square each component, add them together, and take the square root. But sine squared of u plus cosine squared of u is 1, so we're getting the square root of 1, which is 1. Which means that the magnitude of this normal vector is 1, so the normal vector is actually a unit vector. Now, how would we parameterize our function for this particular one? In this case, we take the x component, which is cosine of u, and subtract the y component, which is sine of u. Now we can put this into our integral formula, which would give us the integral from v equals 0 to 2, and the integral from u equals 0 to 2 pi of cosine u minus sine u times 1 du dv. Go ahead and pause the video to work out the value of each of these surfaces' surface integral, then turn the video back on so we can compare our results. For our first surface, the top of this cylinder, we have the function u cosine v minus u sine v, then multiplied by u, which was the magnitude of the normal vector. The u cosine v replaced x, u sine v replaced y. We're integrating from u equal 0 to 1 and v from 0 to 2 pi. You can factor the common factor of u out of the parentheses to give you u squared times the quantity cosine v minus, well, I think that's supposed to be sine of v. So let me get that changed really fast. Looks like this should be sine of v. And when we're looking at this, the next thing we want to do is integrate u squared with respect to u, which gives us u cubed divided by 3, evaluated between 0 and 1, which gives us a constant factor of 1/3 multiplied by cosine v sine v. Then we evaluate this between 0 and 2 pi, which gives us sine v plus cosine v. However, we're in a little bit of trouble because when we evaluate from z equals 0 to 2 pi, 0 and 2 pi are the same location on the unit circle. So both sine and cosine will go to 0, which tells us the value of the surface integral on the top gives us 0. Now, let's go ahead and look at the other two surfaces. The second surface, which is the bottom, is going to be exactly the same because the magnitude of our normal vector is precisely the same. In a sense, it's exactly the same surface, just one at location z equal 2 and one at location z equals 0. Therefore, we're going to get 0 for the bottom surface as well. Now we want to go ahead and take a look at the sides. When we look at the sides, we're integrating over the third surface, which is the outside of the cylinder. And in this case, we have the parameterization cosine u, sine u. And this replaces x and y. So we get cosine u minus sine u. And the magnitude of the normal vector was 1. When we integrate cosine u and sine u with respect to u, however, we get sine u plus cosine u, but evaluated from 0 to 2 pi for u. This is a problem again, since we know that this is going to give us 0. So in essence, the value of the surface integral on all three surfaces is 0. Let's think about why this might happen by looking back at our surface. When we look at our surface, recall that our surface is based on a circle of radius 1. So x squared plus y squared equals 1. And in this case, this means that it is symmetric with respect to both x and y. Our function, which was the integrand part, the first part of the integrand coming way back up here, was x minus y. And since it's symmetric with respect to both x and y, and on circles they maintain the same value, it's not surprising that the surface integral gives us a value of 0. We want to work an application problem for a surface integral of a scalar valued function. What we want to do is we want to compute the mass of some surface, some two-dimensional thing existing in three-dimensional space. We're going to allow our function to be the density function of the material that it's made out of. So say some kilograms per square unit or whatever. Then by integrating the surface integral over the surface, we can find the mass of the object. In this case, we want to work example 5, where a piece of metal has a shape modeled by a paraboloid, where the paraboloid is given by z equal x squared plus y squared, and z varying from 0 to 4. So we can go ahead and take a look at what this looks like by clicking out here on Calc Plot 3D. And we basically have a circular paraboloid, and it is varying from 0 at the origin out to where x squared plus y squared is equal to 4. All right, since z varies from 0 to 4, that means that we have a circle either from a point at the origin out to a circle of radius 2. Now, in order to be on the paraboloid, you have to be on a circle of some radius between 0 and 2, which means that if you're on the circle, then the x and y values have to be identical, which means that x squared plus y squared could be replaced with 2x squared or 2y squared. In that case, since our maximum circle is at the very top when z equals 4, we know that the value of x and y are going to vary from 0 out to the square root of 2, since our circle has a maximum radius of 2. And that's because 2x squared equal to 4 gives us x squared equal to 2. So x is plus or minus root 2. And the same is true for y. So we have our varying values for both x and y. Now, we should parameterize this using polar coordinates. Because we have this circular symmetry going on here about an axis, which is the z-axis, we should be using some form of polar coordinate systems or cylindrical coordinates. When we're looking at this, however, what would happen if we didn't? What would happen if we just did the parameterization where x was u and y was v and z, which was x squared plus y squared, then became u squared plus v squared? We know from our look at our particular shape, the paraboloid, that u will vary between negative root 2 and 2, as will v. So this will get us all the way out to the widest circle with radius of 2, all the way down to the point at the origin. If we do this, then we would need to compute the directional derivatives, the partial derivative of r with respect to u. That would give me 1, 0, 2u, and the directional derivative r with respect to v would give me 0, 1, 2v. Then I could form the cross product of the two to find the normal vector to that tangent plane. When I find the cross product, I end up with negative 2u, comma, negative 2v, comma, 1. To find the magnitude of the normal vector, we square each component, add them together, and take the square root. This gives me the square root of 4u squared plus 4v squared plus 1. Now, in order to go ahead and convert, we also have to parameterize the function. Our original function for the density was given as rho equal to z plus 1. Our z, however, is given by x squared plus y squared, since we have to be on the surface, and x is u, y is v, so this gives us u squared plus v squared plus 1. When we put it all together inside of the integral, we get in the integrand the quantity u squared plus v squared plus 1, the parameterization of the function, multiplied by the magnitude of the normal vector, square root of quantity 4u squared plus 4v squared plus 1 with respect to u and v. And u and v are both varying from negative root 2 to root 2. So while in theory, this definitely works and there's nothing wrong with the parameterization, in practice, this is going to be very, very difficult to actually integrate. A better option when you have symmetry around either a line or a point is to use polar or cylindrical coordinates if it's symmetric about a line, or spherical coordinates if it's symmetric about a point. Let's go ahead and go back and use our polar coordinate or cylindrical coordinate system. In this case, we're going to let x be r cosine of theta, and we can let r be u and theta be v. So this will give us x is u cosine v, and y, which is r sine theta, will be u sine of v. Then we have to interpret what z will be in terms of u and v. Now, if z is x squared plus y squared, so we square u cosine of v to get u squared cosine squared of v. We square y, u sine of v, to get u squared sine squared of v. And we factor out the u squared. That gives us cosine squared v plus sine squared v, which of course is a Pythagorean trig identity. And so it becomes 1. This gives us u squared for our third component. So when we represent it, we have u cosine v, u sine v, and u squared for our parameterization. The next thing we're going to need to do is find the directional derivatives in the direction of u and v, which are replacing our r and theta. In this case, we are integrating with respect to u and v. it's tempting to want to think that this is actually the cylindrical system. So the differential would be r d theta, but that's not quite accurate. In this case, r is u and v is theta, and we are integrating with respect to the surface differential, which is du dv. So it would just be dr d theta if you did not change the variables, not r dr d theta. To find the partial derivative with respect to u, we go ahead and take the derivative of the parameterization, which gives us cosine v sine v to u. Then we find the partial derivative with respect to v, the directional derivative where v varies and u stays constant, which gives us negative u sine v, u cosine v, and 0. Next, we form the cross product to find the actual normal vector of this parameterization. And when we work it out, we get negative 2u squared cosine v in the I hat direction at plus negative 2u squared sine v in the j hat direction plus u in the k hat direction. Remember that when you're finding each one in turn, you can either repeat columns 1 and 2 and use major diagonals minus minor diagonals, or you can mark out each column in turn and row 1 and expand by row 1. To find the magnitude of this normal vector, we square each component, add them together, then take the square root of the result. The first two terms squared give me 4u to the 4th cosine squared of v plus 4u to the 4th sine squared of v. We take out the common 4u to the 4th, getting another Pythagorean trig identity. So the first two terms reduce to 4u to the 4th. Then we add on u squared. We can factor out the common factor u squared to give us u squared times the quantity 4u squared plus 1. The square root of u squared is not u, it's the absolute value of u, multiplied by the radical 4u squared plus 1. Now we want to go ahead and represent this into our surface integral. In order to do that, we have to parameterize our function. In this case, our parameterization is given here, u cosine v, u sine v, u squared. And our equation, our function, the density function, rho, is z plus 1. The third component in the z location is u squared, so parameterizing the function gives us u squared plus 1. We're going to take the u squared plus 1 and multiply by the magnitude of the normal vector, absolute value of u times the radical 4u squared plus 1. When we do this, we can drop the absolute values because u varies from 0 to 2, which means it's always non-negative. Then we can distribute the u across the first set of parentheses, giving us u cubed plus u, all multiplied by that radical. Now, in order to integrate this, we need to go ahead and split it into two integrals. We use the distributive property to get u cubed times the square root plus u times the square root, both integrated with respect to u and v. Both of these are going to require a u substitution, and the u in both cases is going to be the same. It's going to be what's underneath the radical 4u squared plus 1. Since we already have u in play, we don't want to use u again, so instead I've used w. I set w to be what's under the radical, 4u squared plus 1, take the derivative of both sides with respect to u to get 8u du, and then I solve for what I actually have inside of the integrand, which is u du. Now this will work out what I need on the second integral, since all I had other than the radical was u du. But it does not fully take care of what I had in the first integral because I had a factor u cubed. This takes care of one of the u's, but it does not take care of the other two. So I go back to my definition for w equal to 4u squared plus 1, and I solve for u squared. This gives me w minus 1 divided by 4. Then I can rewrite the u cubed du as u squared, which is w minus 1/4, times u du, which is 1/8 dw. This gives me 1/32 times the quantity w minus 1 dw. We also need to change the limits of integration from u values into w values. When u is 0, w equals 1, and when u is 2, w equals 17. We can then replace what we had before with our u substitution, or in this case, w substitution, which for the first integral gives me 1/32 w minus 1 times the square root of w. Then I can think of the square root of w as w to the 1/2 and distribute it across the w minus 1. This will give me 1/32 times the quantity w to the 3/2 minus w to the 1/2. I simply apply the power rule and evaluate it between 1 and 17 to get a value. For the second integral, I'm ready to do the integration after I have made my substitution for w. In this case, I think of the square root of w as w to the 1/2, and I apply the power rule, getting w to the 3/2 times 2/3, also multiplied by the 1/8. Then I evaluate between w equal to 1 to 17. It's going to give you pretty nasty numbers, which is why I went ahead and wrote it out for you. When you do this, you're going to get 17 to the 5/2 power minus 1, all multiplied by 1/80, which is 16 times 5, minus 1/48 times the quantity 17 to the 3/2 minus 1. When you simplify the first one, you end up with 1/80 17 to the 5/2 minus 1/48 17 to the 3/2 plus 1/120. For the second one, when you evaluate, you get 1/12 17 to the 3/2 minus 1. Then you have to integrate with respect to the outside integral, which is with respect to v. There is no factor of v inside the integrand. It's a nasty, nasty constant, but it is still a constant. So when we integrate with respect to v, we just get v, which is evaluated from 0 to 2 pi, which gives us a factor of 2 pi on each integral. Our final result is that it's about 38.4 pi, which is about 120.64. So if our density function represented, say, grams per square unit of area, then this would tell us that this material and that paraboloid weighs 120.64 grams. This is the end of the second video over section 6.6, where we looked at computing surface area and also evaluating surface integrals for scalar valued functions. The next video is short and it is optional. It is taking a look at what's called a Steinmetz solid or a bicylinder. In this, we're going to look at another application of surface integrals over scalar valued functions. If you don't want to watch this one, go ahead and go to the final video on section 6.6, which covers surface integrals over vector fields. See you soon for another video.